let's look at this in a simulation setting. Okay, what we do have here is a loop. See the loop here, we have segment A, B, and then C here, D here. The magnetic field is pointing from north to south, north at the bottom to south at the top. This is a 3D simulation, I can rotate it around. Okay, now this end, okay, the trick is how to show you things without moving things. This end here labeled X is connected to the positive lead of a battery. The bottom end is connected to the negative lead of the battery. Okay, I'm going to remove here, so we remove that from the view. Okay, now like we have seen in the slides, in green here we have the force acting on each of the segments. On segment AB in this case, because the current is going from positive to negative, so it's going from A towards B, our thumb should be in the direction from A to B, or in the same direction of that purplish arrow. The magnetic field, or our fingers, should point from bottom to top in the same direction as these orange arrows representing the magnetic field. So when we do that, our palm is pointing in the direction of the green arrows. That's the force acting on that top segment, AB. Now, for the segment BC, that's the segment here, there is no force because the magnetic field is in the same direction as I. At the bottom segment, I, or the direction of flow of positive charges, is represented here by the purple arrows, the velocity of positive charges. Now in that case, our thumb should be pointing in the direction of that arrow. Our finger should point again in the same direction as these orange arrows, and our palm is going to point in the direction of these green arrows. So both forces are in opposite directions, but they result in a torque in the same direction. I'm going to run this slowly so we see what happens. Okay, you notice that the forces are not going to change. However, pay attention here to the torque. The torque is changing because the lever arm of these green forces relative to the axis is changing. It's getting smaller and smaller. So as a result, we reach a point here where there is no torque anymore. I overshot it by a second, but there is essentially no torque here. And if I continue, then suddenly I have a torque in the opposite direction, plus the negative sign here. Okay. So what's the effect of that? If I run this, this is exactly what happens. And now because of inertia, friction, and so on, this will eventually stop from rotating. And that's what we should observe. Now, however, if you would like to make this into a continuously spinning loop or an electrical motor, what we need to do is, whenever the torque gets to 0, we need to flip the direction of the current so not to allow the torque to become negative. So we keep the torque to be in the same direction all the time. We do this by setting up what we call a commutator. Now the positive lead is connected to this top positive half circle. The negative lead is connected to this bottom blue half circle. In this case, point X, for half a turn, that wire, point X, is going to connect to the red half circle. During half a turn, it's going to connect to the blue half circle. So during half a rotation, the current is going to go into X. During the other half rotation, it's going to be going out of X, making the current through the loop going in opposite directions. By going in opposite directions, it's going to result in forces that are going to reinforce, making sure that the torque is positive all the time. So let's run this. I'm not sure if it's going to run well with this change. Okay, let me reset it. I think that's what it needs. Okay, now we run it here. Okay, and there we go. Okay, now I can stop it here for a second and run it slowly. So look at the forces on the top segment AB. Look at the direction of flow of the current. Okay, now here we are going to reach an area where there is no contact anymore. Now here, when there is no contact, there is no current flow, and no force. It's going to keep on rotating just because of the inertia that it has, the momentum that it has. Now, if I keep going, now X is going to be connected to the negative lead, so the current is going in the opposite direction in segment AB. Instead of from A to B, it is now from B to A. Notice the purple arrow. So look at the direction of the force. It changed from pushing towards the right to pushing towards the left, keeping the torque positive in this case. And that's the idea of an electrical motor, and the secret to it is this commutator. Of course, saying a little bit more about electrical motors, I don't have a simulation here to show you, but you notice that the torque is not at a maximum all the time. To make our motor more efficient, what we can do is, instead of having just this loop, I can have two loops, for example. The other loop would be perpendicular to this one. So whenever the torque on this loop is 0, because the other loop is perpendicular to this one, the torque on that one is going to be maximum. So the overall torque is not going to be 0 at any time. Even more efficient is do a 3 kind of ring pattern. Every ring is at 120 degrees. Now, for each one of these configurations, you need a different commutator. If I have 2 loops, then I'm going to have a commutator that has 4 segments. If I have 3 loops, it's going to have 6 segments, and so on. Okay, let's go back to the theory of this. Now, at that instant that we are showing here, the force on segment BC, I'm sorry, but the labels in here are different than the labels on the simulation, but the force on sections BC and AD are IBW, where W is the length of the segment. We are using sine of phi equal to 90 degrees, equal to 1, because phi is 90 degrees in that case. So the torque due to the loop is going to be, remember what torque is. Torque is F L sine of theta, where this is essentially what we call the lever arm. Now if it's going to spin about the axis, that's going to be due to this one, it's going to be F. If I call the big segment L, my lever arm is just L over 2. And I have 90-degree angle, so sine of theta is equal to 1. So the torque due to this force is going to be L over 2F. And the torque due to this one is going to be L over 2F. So the overall torque is L times F. In general, at any angle, it's going to be L times F times sine of phi. Knowing that F is equal to IBW, we can replace it here. So my torque is ILWB sine of phi. And then remembering that L times W is the area of that loop, then we can write it this way, where the torque is equal to I, the current in the loop, times A, the area of the loop, times B, times sine of phi. One thing that you need to remember is phi is the angle between B and the perpendicular to the area. Okay? This is what phi is. The perpendicular to the area, or the normal to the area, and B, the angle between them. That's important. Now, what the torque tries to do is line up the normal with B. Line up the loop perpendicular to B. That's, I hope, what you have noticed with the simulation. B was pointing up, and what the torque did is lined it up the loop such that it became horizontal perpendicular to B. By having the loop perpendicular to B, the normal to the loop was in the same direction as B. Now this equation, sorry here for the alignment, this equation, even though we developed it for a rectangular loop, the equation works for all types of loops. Moreover, if we have more than one loop that are coiled up in the same direction, then we just multiply the torque by the number of the loops. So my overall equation is NIAB sine of phi. Some other good simulations to play with are the simulation in this side here. So you can change the current, change the magnetic field direction, and so on, and you see the direction of flow of the current. Another simulation, another good simulation is this one as well, from the Florida State University site.